Okay, continuing on with what we have with orthogonal vectors, we have orthogonal projections. And here we had that y is equal to the orthogonal projection of y onto L plus z, okay, where we have z to be a component of y that is orthogonal to the space w, where w is going to be the span of the vectors going from v of 1 out to v of p. And okay, so we have again for our equation, so you have y is equal to the projection y plus z. Again, you have y is equal to the sum of the, you can say we have linear combinations of weights and vectors, and again we have the algorithm for the projection of y onto L representing the line that runs through each vector and the origin. And we have once again our combination, and once again we have y is equal to the orthogonal projection of y plus z, and just taking what we have here from y, and of course the projection y, and we have plus z, and we have from this, okay, have y is equal to the projection y plus z, and z is equal to y minus its projection. And again, you had the projection y and z are going to run perpendicular or orthogonal, geometrically speaking, to each other. And we have in this particular section we have what is regarded as the best approximation theorem, and we have the projection is going to be the closest point in w to y, in the sense that the difference between y and the projection, the magnitude is going to be less than that of taking the difference between y and v, any other vector that is in the span. Okay, and this is again the best approximation theorem. And just looking at what we have, again, so you have the projection is going to be regarded as the closest point, and just sort of playing around with what we have here as an example. So you have 2 by 1 vectors. Okay, we have v of 1 consists of 2, 5. V of 2 we have to consist of negative 2, 1, and we have y equal to 2, 3, and we have in this particular case, all right, so we have to determine the closest point in w to y, and w had to span v of 1 and v of 2, and for the closest point, okay, so we have with the projection, so again we have with our algorithm, you have the dot product between y and v of 1 divided by the dot product of v of 1 and itself. And okay, so for the dot product between y and v of 1 we have 19, and for the dot product between v of 1 and itself we have it 29, and we have plus, have the dot product between y and v of 2, and that will come out to negative 1, and for the dot product between v of 2 and itself, this will come out to 5. Okay, and so looking at the ratio, okay, so you have 19/29 v of 1, and we have plus, okay, we have the next combination, you have negative 1/5, and we have times v of 2 again, which we have at negative 2, 1, and if we add the top and bottom portions together, okay, you have for the closest point, okay, this is going to be at 248 1/45 and 446 1/45, and considering that this is the closest point to y, whereupon we have y is equal to 2, 3. If we look at determining the distance from y to w, okay, in this particular case, all right, so we have for the distance, okay, again we have y minus the projection, and that's going to represent the distance from y to w, and so we have in this particular case, all right, so we have y minus the projection, you have 2, 3 minus again the projection vector, and for the difference this will end up at 42 1/45 and negative 11 1/45, and the distance from y to w is going to be the same as the distance from y to the projection, and for the magnitude in this particular case, right? So you're looking at, again, the square root of the sum of the squares of 42 1/45 and negative 11 1/45, and here you have a pretty outrageous ratio if you leave an exact radical and rational form. So we have the square root of 1885 over 145, or as a decimal to the nearest two decimal places, we have about 0.96. Okay. Also, let's say that if you have a given orthogonal set, okay, still in two vectors, but this time we have each vector, okay, is going to be 3 by 1. And say if we're looking at finding the orthogonal projection of y onto the span of the set of vectors, okay, so you have y to consist of negative 1, 2, 6, and we have v of 1 at 3, negative 1, 2, v of 2 we have at 1, negative 1, negative 2, and for the projection, and just taking what we have here, okay, so we have looking at the dot products, okay, y v1 is 7, v1 in itself is 14, y in v2 has a dot product of negative 15, v2 in itself has a dot product of 6, and just taking what we have for the algorithms and substituting and following through, it turns out that the projection of y turns out to be y itself, where we end up at negative 1, 2, and 6. Alright, now moving along, okay, let's say that if we have working with vectors, say we have let W be the subspace spanned by the given vectors V, and where upon, okay, if we were to write y, which we had to be a 4 by 1 matrix or 4 by 1 vector, where we had 3, 4, 5, 6, and we were to express y as the sum of a vector that is in W and a vector that is orthogonal to W. Okay, now again, W is going to be spanned by the V's, okay, and we have 3 of these. So you have your V of 1, V of 2, and V of 3. And taking what we have for the projection of Y, okay, so we have, again, so you have the dot products, the combinations, and for the first set, okay, you have Y in V1 is negative 22, and V of 1 in itself is 18. For the second set, Y in V2 is 40, and V of 2 and itself has a dot product of 36. And then for the third set, we have Y and V3 with the dot product of negative 16, and V of 3 and itself, okay, is going to have a dot product of 18. And for what we have in this particular realm, okay, so we have just filling in, okay, so we have for the projection of y, so we have substituting, okay, and simplifying what's going to happen here, okay, so you have negative 22 18ths reduces to negative 11 ninths, 40 over 36 is 10 ninths, negative 16 18ths is negative 8 ninths, and substituting the full-fledged vector representation of V of 1, V of 2, and V of 3, and multiplying by the weights, it turns out that for the projection of what we have of y onto L, okay, our closest point, which is going to turn out, will consist of 22 ninths, 13 thirds, 46 ninths, and 53 ninths. And so now, so this is what we have projected onto y. But for a vector that is orthogonal, okay, so if you go back, okay, recall that the projection and z are perpendicular or orthogonal to each other. And again, so we had, this is what we have for the projection of y. Now for z, okay, z is going to be the difference between y and the projection. So for z, okay, looking at the difference, we're going to have 5 ninths, negative 1/3, negative 1 ninth, and 1 ninth. Okay, so for the sum of what we have here, breaking up y, okay, you have the projection along y and an orthogonal vector, so this is what we have for the projection and z, so those are going to be the two vectors in this particular case. Now, if you were to also determine the distance from y to w. Again, the closest point is going to be the projection, again, which we still have 22 ninths, 13 thirds, 46 ninths, and 53 ninths. And now, again, the difference, okay, this happened to come out to z, again, which we had at 5 ninths, negative 1/3, negative 1 ninth, and 1 ninth. And for the distance from y to w, this is going to be the same as the distance from y, okay, to the projection. And so we're looking at the distance to be the magnitude of y minus the projection, which also happens to be, in this case, the projection or the magnitude of z. And so just taking the sum of the squares, 5 ninths, negative 1/3, negative 1 ninth, and 1 ninth. Okay, the sum of the squares will be 4 ninths, and the square root of 4 ninths is equal to 2 thirds, and 2 thirds is going to be the distance from y to w.